Hi, welcome to your lesson on natural logarithms and the change of base. Here's some natural logs. They've been cut down. They're a little unhappy, but you're not feeling like that. You're feeling more like this or like this. You're feeling great about logs. They're going really, really well right now. Let's take a look at something we've seen in the past. We had this special function here into which we put in values of x through 100,000. So we have these values of x that are growing very quickly. When we put those values of x in there, in the function produces these values. So first you can see it's a 2 and rises quickly, but eventually it's not rising so much anymore, and it's actually reaching a limit, all right, 2.718. So even though the x became very large, these values stop increasing. So we said the limit as x approaches infinity, as these values approach infinity, the limit of this function is that value 2.718, because no matter how big we made these, it would just keep getting closer and plateauing at this value. So that's our limit. Graphically, we can look at it this way. As we increase the x values, the y values first increase a lot, and then they just slow down. And again, they're reaching this asymptote of 2.718 because the y values kind of reach that point but never exceed it. Okay, so that number has a very special name. It is called Euler's number, and we call it E. It's just represented by the constant E. We talked about graphing exponential functions with the base E. So here's an exponential function with the base E, and then I can rewrite it like this, right? Because this is just that constant, Euler's constant E, so I'm going to put it like that. That graph is this blue one here. That looks like any other exponential graph. It has a point, it passes through the point of 0, 1, and it has a growth curve here. It is a growth function. Now let's look at what happens when we take logs and mix them with e. So these are called natural logarithms. The natural logarithm is a logarithm with the base e. So now we take a log, just like we did with this last one. We did the exponential function and we did base e. Now we take a log and we put the base e. Instead of writing log base e like this, it can be abbreviated like this, ln x. And the reason for the ln is that it's derived from the French expression logarithme naturel. So again, when you see ln, it just means log base e. And that's just like any other base we put. We put all kinds of numbers as our basis for log. So why not the number 2.718? So we call it e. Okay, so these logs with base e, or ln x, they follow the same rules that we know for logs already. Graphically, let's look at these two. So the red one here is your normal log graph with a base 10. You may remember that they rise like that. There's an asymptote at x equals 0. They pass through the point 1, 0. Same with the blue one, which is now the log base e, or again, written ln x. So there's the graph of ln x. Again, it has the same asymptote, x equals 0. It passes through that point, and it does have it does rise more quickly than the log graph with base 10. Okay, so now using what you know about logarithms, what are the values of ln1 and ln e? And again, think of these as log base e of 1 and log base e of e. All right, so I hope you chose for this one 0 because e to the 0 power is 1. And this one, I hope you saw also there's a base e there, so e to the first power is e. So that would be a 1 for that one. Okay, so now thinking of things that way, let's look at these. I'll help you get started on the first one. We have a natural log of e squared. One mistake that's commonly made here is students, they see this e here and they think, oh, that's like the base e here, but that's not true. We have an e here, but this log here, natural log, also has to have base e. So the e is going to appear twice. Let's take a look. So first, to figure out what this is equal to, we're going to say it equals some value. We don't know right now, but it's equal to x. Then we're going to change this to exponential form. But before that, I'm going to rewrite this log with a base e so I can see it more clearly. So instead of ln, I wrote log base e. So log base e of e squared. And now I hope that can quickly take you to what x must be equal to, or what this is equal to. So taking it to exponential form, e to the x equals e squared. That means x must be 2. Therefore, we know since this is equal to x that this whole expression here must be equal to 2. So that original expression we had is equal to 2. Try that for the second one. In this case, I'm going to set equal to x again. This one begins in exponential form because it's some base to the power here. And this one was log form, right? So this begins in exponential form, so we're going to change it to log form. So I'm going to do log base e of x, log base e of x equals the exponent we see here. So equals exponent. Again, some students, when they see this, they see that log there, and they think right away, oh, log form. No, that's not log form. This is exponential form, so we can change it to log form. All right, now that we have this, of course, this is ln x, so then these are equal. Therefore, x must be 5. All right, and since x is 5, we know the original expression here is equal to x, so the original expression is equal to 5. Okay, try that with the last one now. What form is this, log or exponential form? Okay, this one I set equal to a, and the reason is instead of using x, because I see an x here, so I don't want to confuse that with that x, I'm setting it to another variable. Now this is in log form. This is log base e again, right? So log base e of that equals a. Now change into exponential form, e to the a power, e to the a equals e to, here you can combine these by doing subtraction of exponents, right? So x minus y. So e to the a equals this, which is e to the x minus y. And now we know that a must be equal to x minus y, and therefore the original expression is equal to x minus y, because again, that was what we set a equal to. So there we have that. Those might be kind of tricky at first, but then once you get used to this, how this log base e works, and using the normal rules we've been using, these shouldn't be so bad. Let's look at now, switch gears a little bit to what's called the change of base rule. Change of base rule works like this. We have a log of some base of some value. It can be changed to log of a different base, but notice we have the same base here, of this value divided by log of the new base we're using of this value. So it's always this one on top and this one on the bottom right here, and we have 2 logs. So now we've done a change of base, and that's why it's called change of base, because we start with one base and we change it to another base. So this is useful when you want to change bases to make work easier. So let's use it. We looked at this example, I think, before, but we have this one. Let's say I want to solve this and I didn't want to punch in this base on the calculator, or we have a scientific calculator that only has base 10, for example, and we can change it to log base 10 of 8 over log base 10 of 5. So again, this number on top, this number on bottom, and we change the base to whatever base we want. I chose 10 here so that we can easily calculate that. And of course, when we have base 10, we can just write log of 8, log of 5, because that means base 10. And then we have log of base 7 of e. That one can be log base 10 of e over log base 10 of 7. Again, it doesn't have to be a 10 here. We can do any base we want. That equals a log of e over log of 7. Some students here would choose to use ln, natural log here. So instead of using log base 10, you could have done ln e and ln 7. And the reason for that is, you know, ln e is actually 1. So that could change to 1. If you used ln here, this would be 1 over natural log of 7. But whether you punch it in like this on your calculator or 1 over ln 7, it'll be the same answer. Okay, so let's look at another one here. We have y equals to this equation here, and then we can change that. Oh, sorry, I know what I'm doing here. This is not another problem. This is a proof. It's like, if you're wondering, where does the change of base formula come from? Why does this happen like this? Let's take a look here. So we have y equals this. We can rewrite that in exponential form, a to the y equals x. And now we can actually apply a log on both sides. So if you're wondering, where did that come from? Like, we have this expression as an exponential expression or equation, and then we put this log here. Why can we do that? Well, that's the same as doing this. For example, if we had a to the y equals x, we can multiply both sides by 3, right? We know that in algebra, whatever we do to one side, if we do it to the other side, we're maintaining the equality. So we can do anything to either side. In this case, applying a log to one side is the same as applying a log to the other side. So as long as we do this log base b on both sides, we're still good. That's still an equivalent equation there. So now, by the rule of logs, we can drop that, by the power rule, drop the y down here. And then we can divide both sides by log base b of a to get y to be isolated to get this. And this now, you can see, looks like the change of base formula. Because when we have y equals this, we can now say that y is that part, because that's what we started with, equals what we found it to be equal to. And that's the change of base, right? When we begin with something like this, we can rewrite it as logs with different bases of this number divided by this base number here. So that's kind of a proof where this rule comes from. Okay, so let's see if we can find this. Find the value of log base 3 of 20 to 3 significant figures. And use first base 10, so change it to base 10, and then use your calculator. And then after that, try with base e. In other words, making 2 natural logs here, and see if you can get the same answer. Okay, so if we change that to log base 10, then we end up with log 20 over log 3. Calculate that, you get this. If we decide to do a natural log, you can do ln 20 over ln 3. Again, that's log base e of 20 over log base e of 3. That, if you punch in your calculator, same value. So that's, it might be obvious, but also it's important to know, because a lot of students ask, does it matter what base we put, or sorry, what base we put here? It doesn't matter. The change of base can be used to change to any base we want. And once you do that, you get this answer here, no matter how you set it up. Okay, let's try this one. Okay, that should have been a pretty simple one. You are given an expression here, and you're given that this equals p and this equals q. In this case, we have log base 4 and log base 4. So if we're going to rewrite this expression in terms of p and q, we need to get a log base 4 in there, because that's what we see here. So that, by change of base, becomes this with the log base 4. And then each of those we know is given here, q and p. So we write it like that. So change of base helped us put it in a form where we can match what we're given here and then replace with the variables. Okay, so these ones we're looking at as well in class. Let's take a couple examples here. In the first one, it's simple. We're given log base 4 of a equals b. So this equal to b, this base 4 will be equal to b. And we see a base 4 here. So all we have to do in this one is drop that 2 in front. And then log base 4 of a is b. So we end up with 2b. So that one was simple. But what about b? We looked at that one as well. In b, it's not a base of 4, it's a base of 16, but we need to make it a base of 4 so we can use this here. So that, by change of base, gives us this and becomes b over 2. We looked at these, I think, during our investigation in class, so let's just quickly go through the next one. C, by change of base, becomes this, and therefore we have 2b over negative 1, because that 2 drops in front, so that becomes 2b, and 4 to the power negative 1 is 1/4, so we have negative 1 there. And in D, again, by change of base, we make it base 4. That half goes in front, so half b, and here 4 to a negative 2 power gives 1 over 16, so we have that negative 2 there, which becomes that. Take a look at those. If those were a little quick in class, make sure you understand what happened there, because we have some more coming your way. How about these ones? Now you're given this, this, and you have to rewrite each of these in terms of x and y. So first, I see a base 2. Maybe you need to change it to base a. Try that. So first one, base a, 6 over 2. And then we know each of those values. That is y, and that is x. Try b. In this case, change to base a again, 2 over 6. Just the same as that, but reversed, x over y. And in C, okay, change of base, log base a of 36 over log base a of 2. And then you can, this can become 6 squared, because we have a 6 here, so we have 6 squared. This one is okay, it matches what we have. So that becomes 2, because the 2 drops in front, 2y over x. Here's a few more. Try D, and check your work there. These are getting a little tougher. 24 is made up of 2 squared times 6. These ones, the base does match, so we don't have to worry about changing base. There's that rule. Expand that, and then drop to 2, and you have that. How about this one here, E? Okay, that base was not the same, so I did use change of base here. 12 over 6. 12 is actually 2 times 6. That becomes log base a of 2 plus log base a of 6, and then that becomes x plus y over y. Take a close look at these, pause if you need to. And finally, try F. In this case, I need change of base. I notice that 3 is 6 divided by 2. Division turns into subtraction of logs, and then those match the 3 we have, so y minus x over x. All right, great work. Make sure, again, you're studying these closely. This stuff should feel pretty fluid at this point. There's an upcoming lesson on solving exponential equations. Make sure you take a look at that video as well.